Hello everyone, welcome to this talk about electrochemistry in TEM. My name is Walid Dachraoui. I'm from the Electron Microscopy Center in the Swiss Federal Laboratories for Material Science and Technology in Switzerland. Today I will show you about the electrochemical liquid cell TEM using the setup from Protochips to observe the phenomena at the solid-liquid interfaces in lithium-ion batteries. As an outline for this talk, I will start with a brief introduction. Then I will tell you about the techniques and the methods used for this project, in situ electrochemical liquid cell setup, and the imaging techniques, which is the electron microscope. And then I will give you some results about the solid electrolyte interface growth, and I will finish with a brief conclusion. Let me first tell you about the lithium-ion battery with liquid electrolyte. A lithium-ion battery is formed with three main parts: a negative electrode called anode, a positive electrode called cathode connected with the electrolyte, which consists of a salt dissolved in an organic solvent. During charge, the lithium ions are transported by the electrolyte to be inserted in the anode, and during discharge, the opposite way occurs. If we look close to the interface between the electrolyte and the negative electrode during charge, the lithium ion solvated by molecules approach the interface and get inserted in the anode, and then the molecules are reduced by electrons, leading to the formation of products on the surface of the electrode, which is called the solid electrolyte interface. Many structure has been suggested for this layer, but the most accepted is the mosaic structure composite of different products such as lithium oxide, lithium fluoride, lithium carbonate, and inorganic oligomer. The solid electrolyte interface layer is miraculous because in its ideal case, this layer is insulting for electrons, which can prevent further decomposition of the electrolyte, allowing its stability, and also it's permeable for lithium ions, where the lithium can be transferred between the electrolyte and the anode. However, unfortunately, this is not the case in real battery. The solid electrolyte interface is not perfect. That's why it's very important to study the nucleation, the growth, the evolution, and the structure of this layer in order to find the way how to make it perfect. The challenge of studying the solid electrolyte interface layer post-mortem are related to the preparation techniques that can modify the solid electrolyte interface, because it's air sensitive and fragile, and also some characterization and preparation techniques can have an invasive effects on the solid electrolyte interface. For that, it's very appealing to use in situ Operando characterization techniques to study the nucleation and the growth, the structure of the solid electrolyte interface during battery operation. Here in this slide, I'm showing you the in situ electrochemical setup from Protochips that been used in this project. There is the tip of the Poseidon holder here with a droplet of liquid that can be encapsulated between two e-chips. The bottom e-chip is called spacer e-chip, which contain 4 spacers allowing the control of the thickness of liquid, and the electrochemical e-chip or the top e-chip is an e-chip with electrodes on top of it. Here, for example, the counter electrode and the reference electrode, and the working electrode or glassy carbon is lying in the silicon nitride membrane window transparent for electron beam. Here is shown the way to build the cell using an O-ring and the bottom and top e-chip. After closing the cell, it's possible to flow the liquid and electrochemically cycle the cell. The right here, we have the complete setup for electrochemical liquid cell, where in the zoom in we can see that we have the cell formed with the two e-chips, and the electron beam can go through the window and image the glassy carbon electrode, and we can inject liquid via or using a syringe pump, and we can the microscope used for this study is a Titan Timis with aberration corrector, and we have been using the Z contrast or STEM mode for easy interpretation of the images and movies, and also easy to control the electron dose. For example, here we have a typical high resolution STEM image of the bismuth ferrite compound, where the bismuth and lead appears as bright dots and the iron appears as less bright dots because of its lower Z. For that, it's very helpful to use this technique to control the electron dose in order to don't damage the solid electrolyte interface when it's formed, and also it's very easy to interpret the structure of the layer. So before starting our experimental part to grow Operando the solid electrolyte interface, we made an optimization of the electrochemical and imaging conditions. And here we have the main measurements that made on the ferrocene copper redox to optimize the flow rate and the scan rate, and also the contact between the electrode and the electrolyte. Using different scan rate, we were able to see that we don't have difference between 12.5 millivolt per second and 800 millivolt per second, only a slight change in the current, so we choose it 100 millivolt per second for our experiment. And for the flow rate, also there are no difference between the different flow rates, so we use it 2.5 microliter per minute for our experiment. And with the chrono amperometry and the impedance spectroscopy, we can see that the electrodes are electrochemically connected via the electrolyte. The imaging conditions also were optimized with the electrolyte, and then we can see that with the beam off and beam on with this electron dose, there are no effect or secondary effect of the electron beam on the electrochemical measurements, and also on the electrolyte that we can see here from 0 minute to 10 minutes. There are no degradation or electron beam induced effect on the electron beam on the image. So with that, we were able to optimize and choose the parameter for. So after optimization of the electrochemical and the imaging conditions, we used this electrolyte to grow the solid electrolyte interface. Before cycling, we have the liquid inside the cell injected already, and we can see that we have a smooth interface and surface of the glassy carbon. And then after a few cycles, as can you see here in these CV curves, the solid electrolyte interface is formed, and with this image in the right side, we can see that we have a thin SEI and the surface of the glassy carbon is covered. With that, we are able to form the solid electrolyte interface, and the question is, what is the nucleation and the growth mechanism? So, in order to study the exact nucleation and the growth of solid electrolyte interface, we zoom it in a very local part at the edge of the glassy carbon, and then we start cycling. We can see from the typical CV here that around 0.5 volt versus lithium, we have a peak of decomposition, and during this peak we image it at the interface, and we can see that we have nucleation of nanoparticles. And from the series of image in the bottom here, we can see that before cycling we have a smooth interface and edge, and then after that a nuclei start to grow within the surface and at the edge, and then after that these nuclei participate on the formation of nanoparticles. At the end, we can see that we have a very clear solid electrolyte interface with a continue. So by imaging the interface of the glassy carbon with the liquid electrolyte, we know that at the first cycle that we have nucleation or decomposition of the electrolyte to form nuclei, and this nuclei will grow to form nanoparticles. And then further, after the second and the third cycles, we can see that we have a clear formation of island-like by the agglomeration of the nanoparticles grown via decomposition of the electrolyte, and then these islands like zones start to join each other until they form a continuous layer. Here, for example, in this series of image, we can see that the smooth edge of the glassy carbon start to form nanoparticles after the first cycle, which is related to the decomposition of the electrolyte, and then these nanoparticles start to form island-like regions. And with this island-like regions connection, at the end we can see that there is a continuous layer formed by these nanoparticles. The first cycle allowed at the end to form island-like regions, and then the third cycles, a continuous layer is formed at the edge of the glassy carbon with the thickness of around 160 nanometers. And in parallel to that, we can see that we have formation of bubbles, which can correspond to different type of gas that forms during the cycling, for example, the carbon oxide or PF5. It's very important to understand the nucleation, the growth of the solid electrolyte interface, and also the evolution of this interface layer. For example, here we did the study that we start with a fresh glassy carbon where we have a smooth interface, and then after one cycle we have the peak of decomposition here that corresponding to the formation of these nanoparticles, and then the peak become smaller where island-like are formed on the surface and at the edge, and then after that the peak also becomes smaller than the previous one where we have the continuous SEI layer formed at the edge and at the surface, which is really discontinuous, and also at the end we can see with further cycling that the peak of decomposition becomes smaller and smaller, and then we have a continuous SEI or dense SEI layer at the surface and at the edge of the glassy carbon. So the densification of the solid electrolyte interface is coming with further decomposition of the electrolyte. And then in this high resolution image, we can really see that the formed continuous SEI layer from the connection of the island-like regions allow the covering of the glassy carbon partially, and then we still have access of the liquid electrolyte to the glassy carbon, and then maintain this contact that allow further decomposition, which will make it possible to form the solid electrolyte or densification of the solid electrolyte interface. After four cycles, we can see clearly that we have increase in the thickness and also in the densification or the density of the solid electrolyte interface, and this will block or will prevent further decomposition of the electrolyte, and that can be explained by the decreasing of this peak corresponding to the decomposition of the electrolyte. After that, we have stability and we don't have further decomposition of the electrolyte, and then the solid electrolyte interface is very stable. At this stage, we decide to study the morphology, the structure, and the composition of this solid electrolyte interface. So in order to complete the image or the story of the solid electrolyte interface, first we studied in real time Operando how the solid electrolyte interface grow, and then how it evaluate during cycling, and then the formation of a mature or final solid electrolyte interface layer with dense structure and no further decomposition. For that, we start with EDS mapping to see the element distribution, but in liquid mode this a little bit challenging because we have very thick liquid layer, and also the chips used there has two silicon nitride membranes which have around 100 nanometer thickness together. This will make the EDS mapping or the signal not very good to have a clear image. So for that, we used an ex-situ holder from Protochips, where it's possible to use only one heat chip and then study it inside the microscope. Here is the typical cycled heat chip, and then using the glove box we disassembled the in situ cell, and then we cleaned the heat chip, and then using the ex situ holder we move it in a sealed environment to the microscope, and then after that we start imaging and analyzing using EDS mapping. And here we can see that we have more or less homogeneous distribution of the elements, and with this quantification we were able to quantify at the inner, the outer, and the region on the surface of the glassy carbon. And then the conclusion is that we have a higher concentration of inorganic compounds in the inner part, and the organic compounds dominate the outer part. And this is a typical distribution of elements corresponding to the mosaic layer structure. To complete that, we made with the same procedure or the same heat chip a morphology and structure study of the solid electrolyte interface, and then using high resolution STEM image and SEM, we can see that the solid electrolyte interface is dense, however, still always possible to see some voids, and these voids will allow always the contact between the electrolyte and the glassy carbon electrode, and then we have a slight decomposition which allow a very slow evolution of the solid electrolyte interface, and also degradation and of the electrolyte. With high resolution STEM, we can see that in these regions, the inner part, we were able to detect the three main inorganic compounds, as you can see here from the high resolution or the atomic fringe. And then with the FFT, we were able to confirm that the coexistence of these three elements, which corresponding to the inorganic famous lithium ferrite and lithium carbonate, and also lithium oxide, and this corresponding to a typical mosaic structured SEI layer. With that, I came to the end of my talk, and I would like to conclude. First, using the Poseidon holder from Protochips, allowing electrochemical measurements inside the TM and also in liquid mode, we were able really to shed light on the chemical reaction inside the battery, and that allowed us to, for example, to study the early stage of the nucleation of the solid electrolyte interface, which is very important for battery to know how this layer is formed in order to be possible or to find a way how to make it perfect. We found that the growth of the solid electrolyte interface layer is not one step, but it's multiple steps, where we found that it starts with nucleation of nanoparticles and then formation of island-like layers, which allow a dispersed or non-continuous layer, and then with further cycling we found that we have dense continuous layer is formed by densification. And with that also we were able to study the structure of the solid electrolyte interface and found that we were able to form the mosaic layered structure. If you wanna more information about this project or this study, please go to this paper, and also don't hesitate to contact me with my email that I have showed in the first slide. With that, I came to the end of my talk. Before going to question, I would like to thank all the members of my group, the Electron Microscopy Center at Empa in Dübendorf, Switzerland, headed by Professor Rolf Erni, and the group of material for energy conversion at Empa, Dübendorf, Switzerland, headed by Professor Korsin Battaglia. Also, I would like to thank all the financiers and also Protochips for this opportunity to talk about our recent results. And thank you for your attentions, and you are welcome for questions.